So in this problem, we want to find out when a particle reaches its minimum speed, if its path is given by r of t equals 3t squared for the first component, 2t for the second, and 4t squared minus t for the third, where t is in seconds and the distance is measured in centimeters. So, okay, right away, speed, what are you thinking about? Magnitude of v of t, right? So find that, and then we'll talk about the rest. So what do you got to find first? Inside out, so v of t is r prime of t. So what is that going to turn out to be? 6t, 2, and then 8t minus 1? Okay. And then what is the magnitude of that thing? Square root of, whoops, that's a horrible square root. Square root of what? Okay, 36t squared plus 4 plus, okay, can I square this right away? What would that be? 64t squared, it's squaring a binomial, right? 64t squared minus 16t plus 1. Everybody sees where that comes from? Yeah? Okay. And then, so what do we get underneath that radical? Okay, that's nice. 100t squared for this guy plus this guy. Minus 16t plus 5. So this is the magnitude of v of t as a function of t, right? So this is a calculus 1 type function of t, isn't it? Let's give it a name. Let's call it f of t. Did you want that? Okay, there we go. This is a calculus 1 type function of t, isn't it? So we're really asked to minimize a function. Remember that? Does that ring a bell? You did a lot of that in Calc 1, didn't you? So here's the thing. Do you want to see the hard way or the easy way? Okay. This is a square root of a parabola, basically, right? So would you believe that, well, wherever the parabola hits a minimum value, whatever t value, I'm not saying the minimum value is going to be the same, it won't. But wherever the parabola, the radicand has a minimum, won't the square root of the radicand still be the minimum for the square root function? So you can count on the square root not having anything to do with the input value, where the input value's minimum is. In other words, the t value that produces a minimum for the radicand will be the same as the t value that produces a minimum for the square root of the radicand, simply put. Does that seem reasonable? So long story short, instead of calling f the magnitude of v of t, why don't we call f, why don't we set f equal to the radicand? And then if you like, you could use Calc 1 techniques to find the t value that produces the minimum of this, or you could realize that that's just a parabola that opens up, right? And you could use the vertex formula if you really wanted to find the t value that produces the minimum. But since we're in calculus, let's use calculus. F prime of t, what is that going to give you? 200t minus 16. So do you remember what to do? You got to find your critical value, right? Where the min or max might occur, the relative min or max, or the local min or max, whatever you called it. So you set it equal to, you set the derivative equal to 0. And you're essentially finding the first coordinate of the vertex of that parabola when you do that. So what do you get? You get t equals 16 over 200 maybe, which reduces to what? 2/25. And that's in what? No, well, t is in, No, I think you're just at. Wait, let me read it again. Find out when. Oh, you're looking for t. We're done. Find out when a particle reaches the minimum. T equals 2/25 seconds, so not very long, right?